Hi everyone. I hope you can hear me now, right? Okay. So let's just quickly discuss cyclic redundancy check, which is also called CRC. So we have already uploaded the videos, and I'm expecting that you might have seen those videos. So that is why I will not repeat the theory. Unnecessarily doing the same thing again is not a good idea. So we will directly quickly rewatch or some of the slides that we have already seen, and then we will go to the practice directly. Okay. So cycle codes are one of the kind of linear block codes. Okay, I mean actually the hierarchy is something like this. There is block code that I told you. Inside this block code, there is also something called a linear block code, and then there is the CRC is one of the type of linear block code. Anyway, the hierarchy is not important, so that's why I have not written explicitly anywhere. But yes, this is the hierarchy that is given in the textbooks. So let's just see that how to calculate a CRC for any given data word. So let's suppose that some data is given to you. These are the same slides that we had earlier. Okay. So some data is given to you. Then what you will do, you will, based on the generator, you will add some parity bits. So suppose the generator is having length of 4. Okay. Then the parity bits will be of length of 3, because basically these parity bits are just a reminder. So you will divide with this generator. So the generator, let's suppose 4 bits, then the remainder could be of 3 bits, right? It will be of 3 bits. Basically, it cannot be 4 bits. Okay. So this is what we did, right? Now let's just move to the next slide. So suppose you want to divide this 1001. You want to this was the code word, and you want to divide this 1011. Then first you need to append 3 zeros. Okay, that's how the CRC mathematics will work. And these 3 zeros, you have to append these 3 zeros, and then once you calculate your remainder, so what is the remainder here? It is 110. You just replace these 3 zeros with this 110. So finally your code word is this that you want to send, right? So what you are doing, basically, you are you are having a data word, and then you are basically I mean, in terms of polynomial, in terms of binary, what you're doing, you are appending 3 zeros, and then you're adding this, right? Final remainder you are adding. In terms of polynomial, what you are doing, if you are basically, let's suppose if you are having, let me just go to the polynomial mathematics. So here, before I go to that polynomial mathematics, so here let's just see that how to decode it, right? So how to decode it? At the decoder side or the receiver side, what you will be having, you will be getting the code word. The code word that receiver will also divide with the same data, same generator, and then receiver will check whether whatever you are getting is 0 or not. If it is not 0, then there must be the error that has already occurred. What if it is 0? What if it is 0? Then there may be error, may not be error. Basically, this particular code word is a valid code word. Then you do not know whether the error was there or error is not there, right? I hope you understood. So basically, let me write here. Let Rx is received code word and Gx is generator. And okay, so let's suppose that this received code word will get divided with this Gx, right? So with this, and this is the remainder. Let's suppose this is the remainder that we are getting. Okay, so let me have the options. Option is saying if remainder is 0, then it means no error. Something like this. Okay, you can they can ask something like this, some question like this. They will say that okay, if remainder is 0, then sorry, yeah. So they will say if remainder is 0, then sorry, then there is no error. Okay, suppose this is one of the option. Another option is that if remainder is 0, then there will be error. Okay, suppose these are the options. If remainder is 0, then there is error. If remainder is not 0, let me have another option. If remainder is not 0, then error. If remainder is not 0, then no error. Which of the following are correct? Let's suppose this is MSQ. which of the following are correct? Remainder is 0, then there may be no error. I mean, it is always the case. It is basically always. This always implies no error. Okay, these are the always. So remainder 0, then no, it doesn't say no error. Okay, so if remainder is 0, then maybe error, may not be error, right? So you are not sure. But if remainder is not 0, then you are going to say that there will be error. So that's the C is the answer, right? Okay, great. So let's just understand the same mathematics using the polynomials, right? So in the polynomials, what we do, we are having some binary pattern, and then we are just going to change that binary pattern to the polynomial. So CRC follows a special kind of mathematics that is called modulo to arithmetic. Okay, or module or polynomial arithmetic, module to polynomial arithmetic, something like this. So basically here, every coefficient can be either 0 or 1. I mean, for this polynomial, whatever the polynomial you are having, it could be either 0 or 1. No coefficient could be 2. Okay, so here either coefficient is 0 or the 1. So you know how to convert to the polynomial, right? So similarly, like you can convert this to a polynomial directly, like wherever it is 1. So this is x power 0, this is x power 1, and wherever it is 1, you just write that, right? This is x power 6, something like this. Okay. So now let's just go to the very important slide, which is adding and subtraction. Both are same in the CRC mathematics. So basically here, if you, let's suppose if you do 1 minus 1, it is same as 1 plus 1. It is same as 1 JOR 1. Okay. It is also 0. It is also 0. And it is also 0. Similarly, minus 1 and plus 1 are actually same here. So minus 1 and plus 1 both are same. So if you are writing 0 minus 1, it is same as 0 plus 1, which is same as 0 JOR 1. Okay. So suppose this is one polynomial that you have. This is another polynomial that you have. Suppose you want to add these two polynomials. So it will be x6 plus x5 plus x4, but it will be 2x power 2. It means what? At the second bit, you are basically having 1 here. If you convert that to binary, if you convert that also to binary, the second bit you are having 1. So 1 plus 1 is actually 0, right? Or the coefficient is 2, then you just make it 0. Basically, the coefficient could be either 0 or 1. So finally, you will be having this as polynomial. You can convert that to binary if you want. So basically, if the coefficient is 3, then it is just x square. Coefficient is 4, it is 0. Coefficient is 5, then it is just x square, right? Okay. So let's just see that how you are going to perform the division. Okay, in case of polynomial. If you want to perform the division in case of polynomial, then I think if you have seen the video, then you can do this question very easily. So this is the division, then you will be dividing with the x cube, then whatever you are having, and like that's how you divide. And then finally, this is the remainder, right? So what do you need to do? You will be having your divisor, like your dependent, like to which you are dividing, basically the message or the message polynomial, and then you just append this, which means you will just going to add this in your data word, and then finally you are going to say that this is my code word. Okay, so data is basically x cube plus 1. If data is x cube plus 1, then what you need to do first of all? You need to identify divisor is of which bit. Okay, if see this is x cube plus 1, then first of all what you need to do, so what we were doing in the binary, we were basically appending 3 zeros. So now suppose that this is x, like earlier this was 1 0 1 1, then this means the highest means 0 1 2 3, so it was x cube. But after appending 3 zeros, this is what? 0 1 2 3 4 5 6, this is x6 basically. So basically in this binary, if you're appending 3 zeros, then it is same as saying you're multiplying in the polynomial, you're multiplying with x cube. If you're appending 3 0, you're multiplying the polynomial with x cube. So basically here, if x cube plus 1 is your data word, then you need to first append 3 zeros or 4 zeros based on your divisor. Let's suppose divisor is having of length, I mean the maximum is this 3, so it means the length is 4, right? You need to append 3 zeros. 3 0 append means the x cube multiplication. Okay, how we have identified that we need to multiply with x cube? Because the highest here is x cube, so it means that it is 4 bit, basically in terms of bits it is 4 bits, then you need to append 3 zeros. So that's why it is same as multiplying x cube, or in simply putting, if it is high x cube, the divisor is high x cube, then you need to multiply with x cube. Okay, and then you divide. We can convert polynomial to binary to simplify. No, why you need to do it? I mean, if you want, you can do it. Otherwise, there is no problem. You can directly do with this. I actually prefer the polynomial. You can prefer anything. Okay. So this is x6 plus 1. Then you can do it. This is or should I do it? Maybe you can do it, right? Because we have already done this in the videos. So you just first, this is important, multiply by x cube. Why we need to multiply by x cube? Because this is maximum in division, maximum degree, or maybe let me just say degree of division. Okay, at the end, you always append divisor minus 1. If it is 4, then append 3. Okay, if it is 4, then append 3. If it is 2, then append 1, like that. Number of bits here will be just divisor minus 1. Okay, so let me quickly tell you, if divisor is 4, you append 3, right? Now, divisor is 4 means what? What will be the highest degree of this? This will be x cube, it will be x cube. In polynomial, it means append 3 means multiplying by x cube. Okay, in polynomial, append 3 means multiplying by x cube. So basically, if divisor of 4 bits, append 3 bits, or in polynomial, if divisor of 3 degree, then multiply by x cube. Okay, maximum degree is 3, then multiply by x cube. Something like this. Okay. Now, let's just move to most important part of CRC, which is cyclic code analysis. Okay. So this is very, very important. Let's just say that data word is dx and code word is cx, which means this data word must be added to your maybe like added to something, and then finally you convert that to code word. See, these are the polynomials or the binary representation, that does not matter. In polynomial, what you do, this is your data word, let's suppose. Okay, this is your data word. And then what you do, you have your remainder, you just add that remainder to convert that to code word. So you will be adding the remainder to convert that to code word. Generator is something that is known to sender and receiver both. Right? And then error is something that you get in between. Now let's just take one example. Suppose you are sending something which is 1011. Now the corresponding polynomial will be x cube plus x plus 1, right? Now suppose the error has happened maybe at this place and at this place. Suppose at 2 places error is there. Then it will get converted to 1101. Can you write the corresponding polynomial? It will be x cube plus x square plus 1, right? X cube plus x square plus 1, isn't it? Now, what I want to tell you is that this is this is what you are sending, sender side. This is what you have received, right? In between there was error. So let's suppose at the sender side you have the code word that I am representing by cx. Okay, so let's suppose so let's suppose this is the code word that I'm representing by cx, and at the receiver side, whatever you are receiving, let's suppose I'm denoting that by rx. Okay, and the error is, let's suppose, ex. So basically you are sending something, you are receiving something, right? You may receive exactly same thing, or you may introduce some error. I want to tell you that what is the relationship between sending code word, receiving code word, and error. Okay, let's just check it. Tell me, if I just write this receiving code word is exactly equal to sending code word, okay, in the polynomial form, plus error. So what is the error? Error here is at this bit and this bit. So which means the error, if error is at 2 bit, so error will be represented like this. Error will be, this is this is x power 0, x power 1, and x power 2. So x power 1 and x power 2. So error will be x square plus x. Okay. So if error is happening at 2 places, then it will be, I mean, in these 2 bits, then error is x square plus x. Now let's just check whether this satisfies or not. So which means that whatever I'm receiving, okay, it is basically flipping the bits, right? I have flipped these 2 bits. Now I need to check whether the flipping the bits, does this make sense in the polynomial arithmetic also? Which means, I mean, make sense in the sense, can I write something like this? So what is the receiving end? I have x cube plus x square plus 1. What I'm sending? X cube plus x plus 1. If the error is x square plus 1 plus x, do I get this? See, x cube I have, x square I have, this x and x will make it 0, and then this one I have, right? So I think these two are satisfying. So what do I mean to say? That whatever is your receiving code word and whatever is your whatever you are sending, okay, send at the sending side, these are related by this, which means you are adding the error. and in vice versa also, which means you can also write, let's just check if we can write, actually you can also write something like this. You can say that receiving code word and plus error is just sending code word. Let's just check it. Okay, so what you are receiving, oh sorry, what you are sending, x cube plus x plus 1 is the same as receiving x cube plus x square plus 1 plus error, which is x square plus x. Is this satisfying? I think this will be 0 because 2x square is 0. This will be 1 plus x. Yes, this is satisfying. So basically here minus and plus both are same. Either you write plus ex or you transfer this ex here, which will be minus ex, and this is also same. I mean minus ex and plus ex both are same. Minus and plus here are same. Okay. So how this receiving code word and the sending code word are related with the error is something like this. You add error in the receiving or the sending, you will get another one. So suppose that here I say the receiving code word, okay, receiving code word is Rx. Let's suppose Rx, then can you tell me the relationship between Rx, Cx and Ex? Yes, 2x square is 0. Anything which is something like, see, 4x square is 0, 5x square is just x square. 2x square means that you are basically adding x square weighted weight. Okay, you are basically adding this x power 0, x power 1, x power 2. So you are basically adding this bit 2 times. I mean this was 1 earlier, okay, and this was one another time. So basically corresponding polynomial will be, so let's suppose here this is the weight of x square, this is the weight of x power 1, this is the weight of x power 0, right? So you can have anything here, and suppose you are adding 2 polynomials where weight of x square is 1 1 at both the polynomial. In the polynomial sense it will be 2x square, but in the binary it is just 0, right? So basically in this mathematics we just have 0 and 1 coefficient. We do not have 2 as a coefficient. Okay, so in the polynomial it will be just 2x square, but if you just think in terms of binary, it will be just 0. So that's why if it is 2 it will be 0, if it is 3 then it will be 1. Basically odd coefficient is just 1, even coefficient is just 0. Okay, so now you know the relationship between receiving word, sending word and the error. This is the generator that we have. So let me go to the next page. Tell me, suppose if I have something like this, I mean this is the notation. Tell me if I divide the this cx with gx, then what will the remainder? Whatever I'm sending, if I divide that with a generator, then what will the remainder? Remainder will always be 0. At the sending side, remainder will be 0. I mean, like what you did, you basically have this code word, right? You have this code word which is data word and reminder. Now, if you again divide this code word, this complete thing, right? Not just x power x6 plus x cube. You divide this whole thing. See, do you remember how it works in the mathematics? In the mathematics, you say a equal to maybe b q plus r, right? I mean, you divide this b with q, right? You divide this b with q, and then let's suppose r is the remainder. Sorry, you divide. Let me take a concrete example. So suppose that you have 10 equal to 3 into 3 plus 1. This is the remainder. You're dividing 10, and yeah, you're dividing 10 divided by 3. So this is called the divisor, right? You're dividing 10 with 3. So anyway, what I want to say that let's suppose you are dividing 10. This is the dividend, right? Okay. So if you subtract the remainder, from 10, then whatever you are getting, this divisor basically will perfectly divide that, right? If you subtract the remainder. So here I'm adding or subtracting, both are same. So basically here I'm adding this, okay, I mean I add or subtract, minus or plus, both are same here. So what I'm doing, I'm adding the remainder or I'm subtracting the remainder, both things are same. So then whatever you're getting finally, Then if you divide that with again this division, okay, if you divide this whole thing again with the same division, then you will be getting 0 at the sending side, right? At the receiver, this might get changed. So if you divide with the same generator or the same divisor, then you may not get 0, but sender side you will always get 0. Okay, because minus and plus both are same. If I'm adding, then it means I'm subtracting. So if you subtract this remainder or you add this remainder, you will get the 0. So at the sender side, this is the sending code word. Okay, so this is the sending code word. If I again divide with this, again means like first what I did, I have appended 0, then I have calculated the remainder, then I have calculated the code word. Now I divide this code word with the generator, then I will be getting always 0 as a remainder, right? Now tell me what I'm receiving. I'm receiving Rx. What is the relationship between Rx and Cx and Ex? Can I write something like this? This code word, if you add some error, then it will be Rx equal to Cx plus Ex. If error is in second and fourth bit, then it will be maybe second bit means x1 plus fourth bit means x cube. So ex will be something like this, right? So this is the relationship between received, sent, and error. Now suppose you divide this again with the generator, then will you be getting 0? If you divide this again with the generator, then what you will be getting? You will be getting Cx upon Gx plus Ex upon Gx, which means you will be, this will be always 0, as I just told you. It is 0. So basically it is 0 plus Ex upon Gx. Is this 0? May not be, right? If there is no error, if E is 0, then yes, it is 0. If there is some E, okay, I mean, it depends on E. Maybe E, like there is some E, like which is basically this Gx can divide. Then also it is 0. So when can this division will be 0? Whenever E is 0, then it is 0. Yes, there is no error. Then obviously like things are fine. Even if E is not 0, then also can this whole thing will 0? These are the just remainder. You're getting my point? See, you're dividing with the Gx, then you will be getting this, you will be getting this. So finally, the remainder is 0 plus Ex upon Gx. What is the remainder is of this? It depends on the remainder of the complete thing. So if this remainder is 0, then the complete remainder is 0. If this remainder is non-zero, then complete remainder is non-zero. Okay. So this is very important to understand. This will lead to all of the analysis that we are going to do. Okay. So let's take one example. So this is receive code word. If you divide by Gx, then this is always 0. This may or may not be 0. The second thing. So suppose that this is the code word that I have. Error is this. I got this, right? Then the received will be represented like this. You can understand this with the binary also. This is the same thing that we did in the binary. So that's how this received code word, error, and sending code word are related. Received code word is sending code word plus error. Okay. This could be 0. This could not be 0. It will be 0 Ex if we take Gx such that, I mean, that's how we will be doing some analysis. If Ex and Gx is having that relation, then it will be 0, it will be not 0 for that relation, something like that. Okay, this is the kind of analysis that we are going to do. So basically all of our analysis will depend on this. Now what will I say? This is Rx upon Ex, right? Sorry, Gx. What will I say? That I will say that receiving code word, if this Gx is dividing this receiving code word completely, it is same as saying Gx is dividing this Ex completely, then it will be 0, right? So I will say if Gx divides Ex, then remainder is 0. A remainder of Rx upon Gx, right? This is 0. Then can you tell me whether there will be error or not? I don't know, right? So we cannot detect error. By the way, the CRC can only detect error, it cannot correct error. Okay, so we cannot detect error. Because if remainder is 0, then I don't know, right? If remainder is 0, there could be error, there could not be error. If Gx does not divide Ex, if Gx does not divide Ex, then remainder will not be 0. It means there is an error. We can detect error. Okay. So this will be the analysis that we are going to do. What we are going to say that, okay, if this is my generator, what kind of errors it can divide? I mean, what kind of polynomials it can divide? What kind of polynomials it cannot divide? So given a generator, in all of my analysis, I will just say that, okay, if this is a generator, then what kind of error it can divide, right? For example, suppose your generator is, okay, let's suppose your GX is x power 5. Can you tell me what kind of EX it can divide? EX it can divide could be maybe x. Can it divide x power 4? Can it divide x power 5? Can it divide x power 6? Can it divide x power 7? Tell me. A, B, C, D, let's suppose. Which one it can divide? Which one GX can divide completely? It can divide this BCD, right? It cannot divide x power 4. So basically, I will say if your generator is x power 5, then it can divide this, which means it cannot detect error at 5th position. AX is x power 5 means, sorry, 6th position. AX is x power 5 means error is 6th position, something like that, right? So if your generator is this, then it cannot detect error which is of x power 5, x power 6, x power 7, because it is able to divide, right? If this generator is dividing the error, then this generator cannot detect that error. If generator is not dividing the error, then generator can detect that error, right? So if generator divides error, then it cannot detect error. It cannot detect that error. Okay. So let's solve one question. Given a generator, okay, let's suppose this is a question. Given a generator x power 5, which of the following error it can correct? Which of the following error it can detect? Okay, suppose this is MSQ question. I mean, not tough question, but anyway, let's just do it. X cube, let's just say x power 5. Let's say it is x power 7 plus x power 10. Let's say it is x power 8 plus x power 9 plus x power 10. Okay, tell me. It can detect or it cannot detect. Let's just say it cannot detect. Which of the following it cannot detect? Since it is able to divide this, it cannot detect this. Since it is dividing this also, because you can take x power 5 common, right? As long as this x power 5 is a factor of, I mean, generator is a factor of error, then you cannot basically do it anyway, but you can take x power 5 common. Here also you can take x power 5 common, right? So that is why you can say that it is able to divide this, it cannot detect this, cannot detect this, it cannot detect this, right? It cannot detect all of this. So this is very easy question. Once you understand the concept, you should be able to solve this, right? Now let's solve more question. But before that, let me quickly tell you that what is happening. Basically, I do have a relationship between Rx and Cx and error. Right? I just told you the example that this relationship works, which means if you are having error at 5th position, 6th position, then error will be 5th position, and let's suppose 8th position, then error will be this, right? This will be the error. Now, if you add that in the polynomial form, then you are going to get the receiver, right? Receiving code word. So this relationship holds. Now, suppose I have a generator, okay? I have a generator GX. Then I will check whether, so it will always be 0. Then I will check whether it is able to divide my error or not. If it is able to divide error, it cannot detect that error. That's the only concept that I'm doing. Let's solve one gate PYQ, okay? I mean, exact, it is not exact PYQ, even though I do not remember the PYQ, but it is there in the next slides. But yeah, but let's solve one question which is almost similar to gate PYQ. Let's suppose they are saying generator is this. Then it can detect errors of which form? Let's suppose they are saying cannot detect error. A is saying double bit error. I mean, there are error in 2 bits. Okay, double bit errors cannot be detected. Okay, if error is in 2 bits, then this generator cannot detect. Okay, single bit error, single bit errors. Let's say contiguous 2 bits error. Okay, see what is the difference between double bit? Double bit means any 2 random bit. Contiguous 2 bits means like contiguous bits, like I mean if 5th position then 6th position, like that, right? Continuous 2 bits error cannot be detected. Okay, cannot be detected. And the last option, let's suppose all of the above can be detected. What do you think? Can it detect double bit errors? It is saying double bit error cannot be detected. But let's suppose मेरी जो double bit error है, let's suppose it is x power 7 plus x power 8. Okay, so since my double bit error is x power 7 plus x power 8, which is basically x power 7 x 1 plus x, so or maybe sorry, let's suppose this is x power 9. Okay, x power 8 plus x power 9. Then this will be x power 7, you can take common, this will be 1 plus x square, right? Now this is my error. I need to check whether my generator can detect this error or not. For that, I need to check whether my generator is able to divide this. Can this divide this? It cannot divide this x power 7, right? Because only x square, x cube can divide this x power 7. It cannot divide this x square, 1 plus x square, I think, right? I mean, you can try it out. I don't think it can divide. Okay, so this is x plus 1. Let me write in decreasing order. It will be x, it will be x square plus x. This is 0. Then this is x plus 1 only. Oh, it is able to divide. Oh, good. So it is able to divide, right? If you multiply this 1 plus, so it is actually able to divide, because this 1 plus x square in our case, okay, in our case, this 1 plus x square is just 1 plus x into 1 plus x. Let's check 1 plus x plus x square. Yeah, this is 0. Yeah. So this 1 plus x square is in our mathematics, it is 1 plus x into 1 plus x. Okay. So yes, this is dividing actually. Sorry. So since it is dividing, can this generator detect this error? Can this generator detect this error? No, right? Generator cannot detect this error. Okay. So GX cannot detect the above error because I'm able to divide. But let's just see that if I have, so this is just one type of error I did. Okay, 2-bit error I just did. Let's just see if there is some error that the generator is basically able to not divide. So okay, KS is asking me to repeat it. So what I did, this error is this. I just want to check whether this is divisible by x plus 1. Okay, so for that, what I did, I basically tried out whether I can divide this thing by x plus 1. So I know that x plus 1 obviously cannot divide this, right? I mean, this is x power 7 can be divided by x square, x cube, like that. Can it divide this? If it can divide this, then the remainder will be 0, right? It should be able to divide with one of them. So I found out, like in our mathematics, like this x power 7, I just actually tried this division, and then I found out that actually remainder is 0. Okay, and this is what we call it, dividend, right? Okay, so this is 1 plus x and this is also 1 plus x. So I mean, this 1 plus x square in our mathematics, it is 1 plus x into 1 plus x. Okay, this is what I just find out. So that's why I'm able to say that okay, you can divide. So that is why this is like this 1 plus x is dividing this thing, right? Let me tell you one more way. Okay, let me tell you one more way. Can anyone suggest me one more way? That how to check whether 1 plus x can divide this or not? Very nice way. Yeah. So basically, minus and plus are same. So basically, let's suppose there's a function. Okay, this function, and I want to check whether x minus k divides above function. This is as good as saying that x minus k, I want to check, okay, I want to check x minus k divides this function or not. The as good as saying x minus k is a factor of function. If x minus k is a factor, then it will divide, otherwise it will not divide. As good as saying, right? Now, suppose it is a factor, okay? Suppose it is a factor, then putting that x equal to k will make this 0. If it is not the factor, then it will not be 0, right? So basically, you can directly put x equal to k. So if you want to check whether this x plus 1 divides this or not, so you can just put x equal to minus 1. Since minus and plus are same, you can just put x equal to 1 here. It will be 0, right? 1 plus 1 is 0. So x plus 1 is actually dividing this error. Okay. Now tell me 2-bit error, okay, double bit error, that x plus 1 cannot divide. Let's suppose I and j. In general, if I take x power I plus x power j. Okay. So yeah, I think x plus 1 will always divide this, right? X plus 1 will always divide this. What do you think? I think if I is 0, then it is 1. Even if one of them is 0, okay. I mean here j or I, one of them is greater. Okay, I mean let's suppose I is greater than j or j is greater than I. So doesn't matter. Even if one of them is just 1, then also I think this is dividing. Yeah, I think it always divides, right? Yeah. So I think it always divides. So basically, x plus 1 will always divide this, which means that if you are having 2 bit of error, okay, 2 bits of error, then you are not able to detect it because it is your generator is dividing it. So x plus 1 will always divide it. So double bit error cannot be detected, right? So double bit error cannot be detected. Yeah, that is correct. So A is the correct answer. Everyone understood this? That A is the correct answer. So let's suppose this is MSQ. Let's just check if I'm having other answers or not. Single bit error cannot be detected. No, single bit is x power 5. That can always be detected because you can you will not be able to divide. So you can detect it, right? So basically, single bit means x power 5. So you cannot divide this x power 5 with 1 plus x. So you can detect it. I mean, how to check whether you can divide it or not? Because it is very simple, 1 plus x, you can put 1 here. You will not be getting remainder 0. You will be getting remainder is 1. So basically, remainder is not 0. You are not able to divide. It is a good thing, right? So you can detect basically. Single bit error cannot be detected. This is wrong. You can actually detect all single bit error. Okay. So if let's suppose one of the options is that all single bit error can be detected. Okay. All single bit errors. Can be detected. The answer is actually this one also. It can or cannot detect errors of which form. Okay. So single bit error cannot be detected. No, that's wrong. Contiguous 2 bits error cannot be detected. it cannot detect any bit error, okay, any 2-bit error. So contiguous also, non-contiguous also, it cannot detect because it is always dividing. So that's why it cannot detect. Yes, C is also correct answer. Okay, A, C, D are the answers. Okay, I hope you understood, right? Anyway, let's just go step by step. We have just moved little far. So this was just to give you an idea that you need to check whether the generator is able to divide the what we call error or not. Okay, if that is able to divide, it's a bad news, which means you cannot detect that error. So option A, double bit error cannot be detected. See, any double bit error which is x power I plus x power j. If the error is in I and j, you put x equal to 1, you will be getting 0, which means you cannot detect it. It is able to, you are able to divide this. If you are able to divide, you cannot detect it. That's why you will say that yeah, that is the correct answer, right? Okay, so yeah, 2 means 0, but where do you need 2 here? This is x power I plus x power j. Double bit error means error in 2 positions, I and j. Okay, so what you are not able to understand, double bit error means x power I plus x power j. Now can your 1 plus x divide this? Okay, if you put 1 plus x, yeah, I mean, if you put x equal to 1, it will be 1 plus 1, which is 2, which is actually 0. I mean, this is just a modulo 2. Okay, so yes, this 1 plus 1 is 0 here. Plus 1, minus 1, 1 plus 1, these are same. Okay. I mean, plus 1 and minus 1 both are same. And whenever you are adding or something, then if you are getting more than 2, you just divide by 2. I mean, all even are 0 or all are 1, or odd are 1, right? Okay, so let's see that what should be the structure of gx. Now basically, I mean, the question could be in any way. Given the gx, they can ask which kind of error it can detect, or you have some specific requirement. Let's suppose you want to detect some certain type of error. Let's suppose you want to detect only single bit error, okay, which means error of this form. You want to detect error of this form. Then what should be the gx? Maybe gx could be anything, right? Okay, maybe okay, if you want to detect x power I, then what should be the gx? Can the gx is 1 plus x? I think it will work, right? Because x equal, if you put x equal to 1, it is not 0, it is 1. So if this is your error, then if you want to detect that error, then what should be the gx? Can the gx be 1 plus x? Let me just ask you this question. A, can the gx be 1 plus x to detect this error? Can the gx be 1 plus or maybe, let's suppose this is x power 10, okay, just for the sake of example, let's suppose this is x power 10. Okay. Now can the gx be x power 11? Okay, can the gx can the gx okay, suppose these are the options. Now let's just check which gx is good to detect this kind of error. Okay, so which kind of gx is good? Okay, so first one is saying gx equal to 1 plus x. Now it is actually 1 plus thing is very easy. Like if you put 1 here, you can see the remainder is not 0. Remainder is not 0, so that's why it is good idea, right? You can detect. Can x power 11 can never divide x power 10, so that's why this is also good idea. I mean, it should not be able to divide. Let's just check whether 1 plus x power 9, 1 plus x power 9 can divide or not. I actually don't think, but anyway. Yeah, so you got x as a remainder. It is not able to divide, right? That's why it is also an answer. Okay, let's just check whether x power 8 plus x power 9 can divide this. X power 8 plus x power 9. Okay, let me write x power 9 plus x power 8. Let me write in decreasing order only. No, you got some remainder, right? So you are not able to divide. So that is why D is also the correct answer. So all of these generators are not able to divide this. So that's why all of these are correct answer. Let's suppose I have one more option, which is x power 7. Then obviously it can divide. So that's why it is not the correct answer, right? Okay. Have you understood? Now, let's just instead of x power 10, let's just take it x power I. Okay. I mean, let's just see if I can do some generalization here. Okay. So let's suppose that J and K are lesser than I. Okay. So suppose I have J here, I have J here. I mean, these numbers are lesser than I. Let's suppose some number which is M, okay, or maybe T is greater than I. Okay. Let's suppose this is my question now. So let's just try solving this question. Okay. So basically these J and K are less than I, only XT is greater than I. Now I want to deduct x power I. So 1 plus x can never divide, right? It is checking 1 plus x is very easy. 1 plus x can never divide this. So that is why 1 plus x is a good division. I mean, good generator for me. Can x power t divide? If t is greater, then obviously no, right? See, t is greater than I, then obviously no. So that is why it cannot it cannot divide. That's why it's a good generator. Actually, do you think it's a good generator? Like which one you will prefer among 1 plus x and x power t? A. Why? Because this t is actually dependent, right? You should take x power 12 or not, you should x power 13 or not, it will only detect till 13 or like that, right? T is dependent on I. It cannot divide only if the I is lesser, but it will be able to divide if it is x power 2t, x power t plus 1, right? So that's why it's not very good thing. I mean, I like if I'm saying that I should be having a generator which should be able to detect all the single bit errors. Then can x power t detect all the single bit error? No. X power t can detect all the single bit error if the error is before t, maybe just lesser than t. If error is after t, then it cannot detect it. So that's why it is not very good generator. I mean, it is not able to detect all the single bit errors, but yeah, till x power x power t it can do. Anyway, for this, this is the correct answer. Now 1 plus x power j. Okay. So do you think it can divide or not? How to identify? I don't think it can divide, right? So maybe you can take, now you can take a concrete example. Let's suppose this is x power 10. This is 1 plus x power 5. You can check it is not able to divide. I mean, it will not be able to divide because of this one. Actually, the problem is that it will be dividing the first thing only till x power 5, but then you will be getting the extra term because of this one, right? This is x power 5. So this will be a problem. So you cannot divide 1 plus anything to this, because whenever you are trying to match, I mean, whenever you are having x power 5 here, then because of this one, you will be having another term. So that's why you cannot divide it, right? Okay. Yeah. One second. I deleted something, I think. Okay. So basically we were here. Now it also cannot divide. So I think this is the answer. Can this divide? I don't think, right? Whenever you're trying to match one of this to I, then another term will create a problem. You're getting my point? Whenever you are saying that, okay, x power, whatever it is, you're trying to match this j with this I, then the another thing will be leading you to the remainder, right? So that is why it also cannot divide. So that's why it's a good generator. And what about this? X power j. So Yeah, if j is less than I, then it can divide. So that's why it's not a good generator, right? So anyway, like given the options, I hope you can able to identify that which one is correct option. We'll just try division, okay? Just try dividing. If it is able to divide, not a very good generator. So here, if you want to detect all the single bit errors, okay, then x power for this, the errors will be in x power I form. Then I think 1 plus x is good generator, right? Or maybe x power I plus something is also good generator. But again, it will depend on I or something, right? Okay. Yeah, x power I plus something. Maybe let's suppose that I say that I want to detect x power I. Okay. For x power I can say any two terms should work मेरे हिसाब से. Okay. Any polynomial having two terms. Polynomial. Okay. This gx will work. Basically, it does not depend on I. I mean, you can take more than I also. Let's suppose this is x power 10. Okay. You can take any polynomial which is having two terms. Okay. Anything. Maybe here 11, here 10, does not matter, because if it is 11, then anyway it cannot divide x power 10. So like any polynomial having two terms, maybe lesser number also, 1 plus x, it cannot divide it, right? The reason being is that whenever you try to match this x with x power 10, another term will create a problem, right? That's the problem. So that is why any polynomial having more than one term will not be able to divide it for sure. So if you want to detect single bit error, then any polynomial will work that is having more than one term. And then what is a good polynomial, like y to divide or y to have much complexity? Then I think 1 plus x is good one, right? Is simple, short and simple. I mean, it is just a small polynomial, so I may prefer this, right? Have you understood this? So any polynomial more than one term should work here. If you for the single bit error detection. Okay, now let's see some more example, right? If there has been single bit error, then I determines the bit position. Gx contains two or more terms, right? Two or more terms. It will never divide into ex. So all single bit error will be detected. Yes, two or more terms will work. And what is the simple and shoot example? It is 1 plus x. Okay, so maybe 1 plus x is just short and simple. Great. Now let's like we have already done it. So I'm just copying. I have just copied those slides. So let's just try to understand this one more time. So what they're saying, which of the following, this is the frozen question. They're saying which of the following gx value guarantees that single bit error is caught. Anything that is having two. Okay. So anything that is having two polynomial, right? Two isolated single bit error. Isolated means like that could be independent. Okay. Suppose that those errors are at I and j. So the error is of this form, where I think at j is greater than I, right? J is greater than I. Yes. Not conjugative, maybe conjugative, may not be conjugative. I don't know, right? So, I mean, these are independent. Now, we want to detect this error, which is x power j plus x power I. Okay. So, what do you think? What should be the generator? Can you give me some example of generator? So, here, this x power I you can take j minus I plus 1. What is a bad generator? I think x power I is a bad generator, right? Hmm. Okay. What is a good generator here? What do you think? You want to detect this kind of error? Okay. Tell me, can x power t plus 1 divide this? I will be checking the condition on t, but I think it cannot divide this one, right? Obviously, it cannot divide this one. because it is just one term. These are two terms, it cannot divide. It may divide this if t is j minus I. Otherwise, it cannot divide, right? Yeah. So if t is j minus I, it may divide this, but it cannot divide otherwise. So if I say that this is my error, okay, this is my error, and this is my generator, then for t equal to j minus I cannot detect this error, otherwise I can detect this error, which means the value t which I'm setting here, only at two particular situations where I'm having the error, I mean two particular combination of I and j. Let's suppose t is 5, then if t is 5, then it cannot detect error. Two errors, if one is at this position, 0th position, another one is 5th position, something like this. I mean, similarly, one is at first position, another one is 6th position, something like this. If the error distance between the error is exactly 5, then it cannot detect that error. Let's just see the slides. What do I have? So they're saying find the status of following. So this is just one analysis that we did. Okay, there is I don't know if there is some concrete idea that I have written here. So this is just some analysis. Maybe I can say x power t plus 1 will not be able to divide it. I mean, it is anyway not dividing this x power I, but it will not be able to divide the remaining one, which is x power j minus I plus 1. If t equal to j minus, if t is not equal to j minus I, it will not divide. If t equal to j minus I, it will divide. Okay, just some simple analysis, so that it is just helping us to see what they are asking. So in this example, they are saying find the status of the following generator related to two isolated single bit errors. Okay, x plus 1, okay, can x plus 1 two isolated single bit errors? Can x plus 1 detect two isolated single bit error? See, isolated single bit errors means it is a form what? X power I plus x power j, right? So one second. Yeah. So basically, two isolated single bit error means x power I plus x power j. Tell me, can 1 plus x always divides or always does not divide? So I don't know. Maybe if it is conjugative, maybe let's suppose I take x power I or j common or anything, x power I common, it is x power j minus I plus 1, right? I mean, let me just take a simple example. Let's suppose x power 4 plus x power 5. Okay. Are these two bit error? Yes. If it is conjugative, which means this is x plus 1, then this x plus 1 is able to divide, this generator is able to divide this error, so it's a bad generator, right? So x plus 1, since x plus 1 is able to divide 2 bit, I mean some errors of this form, that is why it is not able to detect all the 2 bit error. Which kind of 2 bit error it is not able to detect? The errors which are having exactly distance of 1 because of the x power 1. Okay, so it is not able to divide, it is not able to detect any alt or maybe any role, it does not matter, all 2 bits error, all 2 bit error, it is not able to detect all 2 bits error if all 2 bits error of the distance 1, right? Okay, great. Tell me, is this able to detect all 2 bits error? What if x plus 4 plus 1, this is the factor, which means let's suppose your error is x power 7 plus x cube. Okay, suppose your error is x power 7 plus x cube. Can you detect this error with x power 4 plus 1? No, right? This x power 4 plus 1, I mean, if you take this x cube common, then it is a factor, basically you cannot detect. So which kind of error you are not able to detect? The errors which are exactly 4 distance apart, right? So the errors, 2 bit error exactly 4 distance away. Yeah. Similarly, you cannot detect this one if j minus I is exactly t, which means if it is exactly t distance away, if this error and this error exactly t distance away, then xt plus 1 cannot detect that error. If it is exactly one distance away, x plus 1 cannot detect those kind of errors. If it exactly 4 distance away, x power 4 plus 1 cannot error those kind of errors. Let's just check whether this x power 7 plus x power 6 plus x power 1 plus 1 can detect those errors. So I have 2-bit error, which is something like this. I want to check whether x7 plus x6 plus 1 can divide this or not. It can divide only when this thing has this as a factor, right? So since there are only two terms, I don't think that it can have this as a factor. But how to prove it? See, I need to check whether it can divide this or not. So let's just try to divide. Maybe this is one of the idea, or maybe we can have some other intuitive idea. Yeah. So since these are, like, you can say these are the three terms, these are two terms, it will never be able to divide. How? Let me just tell you the intuition. See, this is x power 7 plus x power 6 plus 1. If these are the three terms and these are just two terms, you can never divide it. Why? Let's just see. Let's just see if we try to divide, then what is happening. Okay. This is x power 7 or maybe three terms. What you will do, first you will try to match with this x power j, maybe whatever you write, okay, x power j minus 7 or whatever. So it doesn't matter, but yeah, first you will try to match with x power j. Then you will say there will be two more terms, which is x power something, right? X power something plus x power something. Then here you will be writing how many terms you will be writing. This will get cancelled off, and then you will be writing this term, this term, and this term. Three terms again. Okay. Yeah. So basically, what I'm going to say, like, you will be writing either two terms or either three terms or maybe just one term. This one. I mean, this is, if this becomes x power I, you will not be writing this. If this is not x power I, then you will be writing x power I, this and this. So let's suppose if this is the only term that you are going to write, then obviously this is the one term, these are the three terms, then you will not be able to divide. If let's suppose you are even writing three terms, okay, then in this case, this is the same thing. I mean, by the repeatedness, I can say it will be the same thing. Then if it is three term, then ultimately I have to arrive at the one term at the last. So basically, either I arrive with the three terms, which all of these are lesser than 7. I mean, this is x power 3, x power 2, or something like this. All of this is lesser than 7. Or if I arrive at one term, then also I cannot divide. So basically, if this is having more term, this is having less term, then I don't think we can ever divide, right? So anyway, you can convince yourself and we will not be able to divide. Okay, so Alap is saying that we can't always say this because x cube plus x square plus x plus 1 is able to divide x cube plus 1. Okay, let's just check it. This is x cube plus x square plus x 1 plus x square plus x plus 1. Okay, then you are able to divide. Yeah, that is right. Okay. Yeah, that is right. So here you are able to divide. Yes. So what should be the condition that I should be having to not divide, basically? Okay, I will conclude everything, but I think we need to check it more formally, that whether I can divide or not. See here, why you are able to divide? Because once you multiply by the x, you are getting this. Okay. I think we can check it more formally, which in the sense that we need to check with this as it is coming in my mind. That's the only way here. We might need to actually divide and see whether it is working or not, or what else you can do here. If you multiply this by something, can you get this? If you multiply this by something, let's suppose, okay, this is x power 7 plus x power 6 plus x plus 1. I want to check whether this thing is having a factor of this into something. Can I have something like this? So here must be x power j minus 7, something like this, right? Because I need x power j. And then something extra I will be having, right? And that, let's suppose this is fx. So this will be x power j plus x power j minus 1. I want to check whether this whole thing could be xi or not. Okay, so this will be x power j plus, if you multiply by this, x will be x power j minus 1 plus x power j minus 7 plus fx multiplied by the whole thing. So this whole thing should be x power I only. Fx multiply this whole thing. Can this whole thing be x power I? Maybe I can do some jugaad such that the whole thing is x power I. I don't know. Maybe we need to analyze this more carefully. Okay. In the book, actually, they have directly written, but oh, okay. There is some standard result, I think. So, I mean, we do not need to do it. Let's just check the next slide. If I do have that standard result with me. So the way I have analyzed it is, okay. I have said that, okay, I directly said in this in the recorded video, but I think we need to analyze this more carefully, or otherwise actually there are some standard results that this kind of polynomial, this is some special polynomial. I think that's the only polynomial that does not divide it. Okay. I mean there are many polynomials, but it is one of them that does not divide x power j plus x power I. So there is some standard results I might be having. If I'm not having, then I will just copy that from the book. If there is an odd number of bits, okay. There is some standard result that I will I mean some polynomial that does not divide x power I plus x power j. We do not need to check it, we can just remember it. Okay, I think I do not have it currently, but I will just copy from the book. Okay, so let's just see if we can have odd number of errors, which means if I'm having odd number of errors, then what kind of polynomials are good for it. Okay, so let's just see this. If I want to detect odd number of errors, so for the odd number of errors, what do you have? You have, let's suppose this is I mean, you have errors at either 3 positions or 1 position, something like that, right? So the maximum degree will be odd, right? I mean, okay, you have the errors, let's suppose 1, 2, 3, 4, 5 positions, and one of them is x power 5, x power like you have the error at maybe 6 position, that's why this is x power 5. You have the error at 4th position, that's why you have written x power 3, something like that, right? You have error at 0th position, that's why you have written 1. So basically the total number of terms in this error will be odd. 1, 2, 3, 4, 5. Yeah, so total terms here will be odd. Now tell me, can x plus 1 be ever factor of this? Can x plus 1 divide it? You put 1, then it will be 1 plus 1, odd number of times 1, 5, right? So 5 is just 1 again. So that is why x plus 1 can never be a factor of this. I mean, x plus 1 can never divide it. So I can say all odd number of errors can be detected by x plus 1, right? All odd number of errors. So, and any odd number of errors, ex contains odd number of terms. Interestingly, no polynomial with an odd number of terms has x plus 1 as a factor in the modulo 2 system. By making x plus 1 as a factor of gx, or the gx is just x plus 1, or maybe gx is having x plus 1 as a factor, which means x plus 1 multiply by some other terms also. Okay, then also it will work. we can catch all odd number of errors, right? So basically it is very simple. I mean, you just need to check whether you can divide or not. That's all you need to do. Let's solve one gate P by Q. So what they're saying, GX, it is a generator in the CRC checking. What is the condition that should satisfy GX to detect odd number of errors? So GX, if you want to detect all odd number of errors, then 1 plus X should be a factor of GX. This is correct. Suppose this is MSQ. Then what else? GX has odd number of terms. No, if GX is having odd number of terms, doesn't mean that it cannot divide. Let's suppose this is your EX. Okay, anything. Let's suppose these are the odd number of terms where I'm having error. So having GX same as this will divide this EX, right? If GX is having just odd number of terms, maybe if GX is X, it will divide this, right? So just one term, or maybe just three terms, which is X plus X power 4 plus X 5, it will divide this. So no, this is not the correct answer. GX does not divide 1 plus XK. Okay, so they're saying that if GX is such that it is not having 1 plus XK as a factor. GX has more than 2 terms. No, this is also wrong, right? I mean, if GX is having more than 2 terms, then it can divide. I want that it should not be able to divide. So they are saying GX will not divide this EX if GX does not divide 1 plus X power K. So basically, I can rewrite this to something. I can take X common, 1 plus X power K plus, I mean 1 plus X power 3 plus X power something, right? X power 3 plus X power square. I mean, I can always write odd number of errors, something like this. If it is plus 1 at the end, maybe plus 1 at the end also. Okay, so here they are saying that all GX that does not divide. I mean, if 1 plus, if GX is not dividing this 1 plus X power K, then it will also not divide this. No, right? Maybe GX is this one only. Okay, so like most probably it will not divide 1 plus X power K, right? So if GX is not dividing this, then GX will also not divide this. No, that's not true, right? So I don't think it is true. So that is why only B is the correct answer. I mean, you need to just check it with carefully. Okay, once you understand the concept, then you need to analyze the options in the exam. That's the only way to do it. You just need to produce some counter example. Maybe it will not be quite tough. It will be easy only. Okay, let's just solve more problems, and then you will be able to understand it more. So here, do you understand that why I'm saying that? See, they are saying GX is such that it does not divide 1 plus X power K. And what is my requirement? My requirement is that GX to detect odd number, I mean, GX should detect it. My requirement is that GX should not be able to divide this. GX does not divide this. Right? This is my requirement. And they are saying if GX does not divide 1 plus X power K, then it also does not divide this. No, it is not true, right? Let's suppose GX is this, which does not divide 1 plus X power K. Then it also does not divide this. No, that's not true, right? GX has 1 plus X as a factor of GX. So if 1 plus X is a factor of GX, then GX does not divide this. This is my requirement. If 1 plus X is a factor of GX, then I know that GX does not divide this. That's what we have seen. So that's why I will say C is the correct answer. Now let's see worst errors. A sequence of consecutive bits error are called worst error of length L. Okay, which means let's suppose there are 1, 2, 3, 4, 5, 6, 8. This is the data, and I do have sequence of consecutive errors, sequence of consecutive bits that got affected. Maybe this is called burst error. Okay, what is the length of this? 1, 2, 3, 4. 4 is the length of this. Now let's just read this paragraph that I have taken from Frozen. So this is the paragraph, one of the paragraph in the Frozen. So I have just taken that paragraph. Let me just read this. So basically, for the burst errors, like there are certain things that I mean certain kind of generators that can detect those burst error or not. So we are just going to analyze this, okay, with this paragraph. Yeah, I have divided that into 2 parts. Let's just quickly read it, what they are saying. So they are saying the burst error. Now let's just extend our analysis to the burst error, which is most important of all. A burst error is of form this. Okay. So which is x power j plus, I mean, it is contiguous basically. X power j plus x power j minus 1 plus x power j minus 2 till x power I. Contiguous errors. Okay. Note the difference between the burst error and the two isolated single bit errors. Okay, you can note the difference. So burst error and isolated single bit error are different. It could be at any distance, but burst error should be contiguous. Okay, burst errors are any length of contiguous errors. The first can have two terms or more. The second can have only two terms. We can factor out x power I from here. Write down that just as 1 plus till this x power j minus I. Anyway, it is just saying that burst error is of any length. Okay, I mean any length L, and the contiguous, it has to be contiguous. Yeah, more than one bit, but we are just going to redefine it. We are just going to say if it is conjugative bits error, then I'm calling it a burst error. Okay. Then okay, so if we are having any burst error, let's suppose x power j plus x power j minus I, j minus 1, something like that, right? X power I. So we can always take x power I as a common. I mean, whatever is the minimum, we can take that as common. So suppose that I have I have x power 5 plus x power 4 plus x power 3. This is my burst error. Can I take x cube as common? I think I can take x cube as common. X square plus x plus 1. It will be x square plus x plus 1. Now what they are saying, if our generator, okay, so which kind of generator can detect this kind of error? If generator is x cube, can it detect it? I don't think, right? If generator is x cube, it will be able to divide. It will not detect it. If generator is maybe this x square plus x plus 1, then it will not detect it. Something like this, right? Okay. So they are saying generator can detect a single error. Minimum condition for the generator. If our generator can detect a single error, then it cannot divide x power I. Yeah. So let's suppose my generator is 1 plus x. Okay. Then can it divide 1 x cube? No, right? I mean, 1 plus x cannot divide x cube. Okay. So they are saying that if it is not dividing this, then it cannot divide x power I. What we should worry about the generator that divides it. So basically, we can easily, they are saying that we can easily control my generator such that it does not divide the first term. I should not be able to divide this, should not be able to divide this. They are saying we can easily have a generator that does not divide the first term, but we should more worry about the generators that divide the second term, which is this. Okay. In other words, the remainder of this must not be 0. Note that the denominator is the generator polynomial. We can have three cases. Okay. So basically, what they are saying that any worst error, okay, if this is the worst error, then you can just rewrite this worst error something like this. Let me tell you what they are saying. So they are saying you take this x power I as a common, you just rewrite this worst error. Okay. You just rewrite this worst error. Now what they are saying, there are two terms in this. First is this, another one is this. They are saying that first term, controlling the first term, you should not be able to divide first term and second term. Controlling the first term is quite easy. Okay. Controlling the first term is actually not tough, but we should worry about the second term basically. Okay. So let's just worry about the only second term. Let's suppose the first term, we can easily have a generator that does not divide the first term. So let's just see if I can control the second term. So what is the second term in generic form that they have written? I think this is this one, right? Okay. This is the second term. I mean, these are the two terms that I have. So worst error is always of this form, the first term and the second term. Is this okay to everyone? Let me know. Have you understood what is a worst error? Worst error here in this case is contiguous bit of errors, right? Now what they're saying is that you are having contiguous bit of errors. That's why you are having something like this. Then you can rewrite it in this form. Now, first is let's not worry about the first one. Let's just more focus on the second one. We will decide our generator based on the second term, and most probably if it is not dividing it will not divide this also. I mean, we can adjust if that's the case. Okay. So we will be deciding our generator basically mostly based on the second term only. Okay. So let's just see. So they are saying if j minus I is less than r. Okay. What is r here? The remainder can never be 0. One second. What is r here? Okay. The generator they are talking about. Okay. In other words, the remainder of. So the generator they are talking about is they are taking generator this. So this is the generator they are taking. They are also taking the contiguous bits in the generator. They are saying that, okay, let me take this as a generator, which obviously does not divide this x power q, right? I mean, why I'm able to say this? Because this is just x power q. If you are having generator which is x power r plus something, and then once you match this x power r with x power q with some help, then you will be always having the remainder. So obviously it does not divide x power q, right? So let's just take a generator which is this, and I'm sure that it does not divide x power q. I want to make sure that this generator also does not divide this. Then let's just have some conditions that on what condition this generator will not divide this. Is the objective clear to everyone? What we want to do? So there was a worst error. I'm saying worst error will look something like this. Then I assume that, let's suppose generator is this. Then I want to have some analysis. What should be the relationship between generator? I mean, how should I be choosing this R and what should be the case? Okay, what should be the relationship between generator and the error that I want to detect? So they are saying if j minus r is less than r, j minus I is less than r, which means this r is too big. Let's suppose r is 500. Then obviously this is big polynomial. It cannot divide. The remainder can never be 0. Okay, so we can write j minus I equal to L minus 1, where L is the length of the error. Okay, so here this is 2, then error length is actually 3. So basically j minus I is L minus 1. I mean, if this is the error length, worst error length is L, then j minus I is actually L minus 1. So they are saying that if j minus I, okay, j minus I is lesser than r, which means r is greater, then j minus I is just L minus 1 lesser than r. They are saying that if r is greater than L plus 1, which means if generator that you are having here, okay, let's suppose this is greater than your length plus 1. This is greater than length plus 1, which means let's suppose your burst length is 5. Okay, the error length could be 5. Then your generator, let's suppose, is x power 10 plus x power 9 plus x power 8, something like this, right? If this is your generator, then it can always detect all the errors of burst length 5. You getting my point? So what they said that there is a burst error of this form. Okay, let's suppose x square plus x cube plus x 2 plus x power 1 plus 1. Okay, anything. Okay, suppose of this form. I mean, this should be contiguous. Maybe you can drop 1 or 2 from the last, but it should be contiguous only. Okay, so you can write your burst error something like this. Now what I'm saying, I'm going to have a generator gx such that it does not divide this, also it does not divide this. Okay, also it does not divide this. Let's have a generator which should not divide this and this. So let's say my generator is this, contiguously till 1. Now first thing I satisfied that this generator can never divide the first term x square or any x power t. Okay, are you all convinced with this, that this generator cannot divide this x square, right? Why? Because if you try to divide the x square, then or any x power t, then once you match this with x square, then whatever you are getting will be just remainder, because I mean, this will be this one, and this can never divide. I mean, this will be this one, and this will be just a remainder. Okay, so I have taken care of the first thing, that this generator is not able to divide this. Now we need to take care of the second thing, that this generator should not also be able to divide this. Okay, should not be also able to divide it. Now what they are saying is that, suppose, okay, in general, basically it is x power j minus I till 1. This is x power I. So they are saying, suppose my burst error length is L. Okay, if my burst error length is L, then this L and j minus I are related something like this, L minus 1 and equal to j minus I. I mean, this is very trivial relation, that if this is L length, then if it is 3 length, okay, sorry, 2 length, if your burst error is of 2 length, then this j minus I will be 3, your burst error, okay, x power 5 plus x power 4, should it be plus 1 or something? J minus I is 3. Okay, you need to take x power 4 common in this case. I mean, at the end it should be just 1, right? Okay, so let's just say that I mean, at the end, it should be just 1. But in that case, it will not be contiguous. So let's just take some contiguous thing. Okay. X power 5 plus x power 4. Now just take x power 4 common. It will be x plus 1. Yeah. So here j minus I is just 1 and L is 2. So that's why, I mean, it is just 1. And I mean, there is two worst error, 2 length worst error, but this will be just 1. So basically j minus I is related to L, something like this. Okay. Now let's just check under what condition this generator should not divide my the second term. Okay, so generator is x power I. Now obviously, if R is greater than the second term, which is j minus I, then it can never divide. Right? This is the first case. Okay. So instead of j minus 1, they want to write actually L. So that's why they are saying R is greater than L minus 1. Then it can never divide. That's what they are saying. Which means if we are having a burst length equal to 6, then any generator and what is the condition here? R is greater than j minus I, right? R is greater than L minus 1. So any generator of R is greater than L minus 1, which is 6 minus 1, R is greater than 5. So any generator which is having R greater than 5, which means x power 6 plus x power 5 plus x power 4 plus x cube till 1, right? Any generator of this form will be able to detect all the burst error of length 6, right? Similarly, any generator of this form will be able to detect all the burst length of length 6. Basically, R here in the generator, R here should be greater than this 5. Then you can detect. This is the first condition. Under what condition also you cannot divide this thing, cannot divide this one. Okay, cannot divide this this j minus I. This is what we want to analyze. So the second case is saying, in some rare cases, if j minus I equal to R, which means here, if you go here, yeah. So j minus, let's just take the second case. J minus I means this one x is equal to R. Okay. So yeah, suppose this is plus x cube. Let's suppose the burst length is 3 this time. Okay, which is same as you take x cube common. So I'm now going to analyze the second case, right? So let me remove the first case. So first case was over. Now let's just quickly analyze the second case. So what was the first case? First case was saying if your generator, this R, is basically greater than this 2, right? If it is greater than 2, then you cannot never divide this. Or maybe if you want to write down in terms of L, you can write down, but you can also say that if this generator R is greater than 2, okay, R is greater than 2, this was the case 1, then GX never divides. Okay. Second case is saying that this R is exactly equal to 2, which means this is also x square plus x plus 1, which means this is R is exactly equal to 2. Then this term and this term are same, right? Always same. This term and this term are same. Then GX always divides. E, right? Error. So this is the second, which is basically very rare. Which means once you fix the generator, it is very rare that if you are also fixing x square plus x plus 1, and you also got error that is having x square plus x plus 1 as a factor. But anyway, like you cannot detect all the errors of this form. Which means if your generator is x square plus x plus 1, then you cannot detect worst error which are having x square plus x plus 1 as a factor, right? So which means if R equal to 2, then GX always divides. Third case will be if R is less than 2, which means this thing is just less than 2, maybe x plus 1, something like this. Then let's just see the third case. So the third case is saying in some rare cases when j minus I is greater than R, the syndrome is 0 and the error is undetected. Okay, in this case also they are saying error is undetected. It can be proven that in these cases the probability of okay, probability I will check later. But if your generator is this, in which R equal to 14, oh, in the generator, they are not having the contiguous terms. They are having x power 14 plus 3 plus 1. Okay. So here, okay, generator is not having the contiguous term. Anyway, let's do one thing. Like I think it is not important, so let's not waste our time too much on this. So maybe based on the question we can solve these kind of questions. I mean, based on the options, right? So let's just do one thing. Let me quickly go to the questions. Let's just solve questions directly. If in the questions I do have something like this, then we will be trying to solve it. Okay. Yeah. So let's solve this question. Which of the following generator guarantees the detection of an odd number of errors? Okay. For each divisor, explain why or why not it guarantees the detection of odd number of errors. So tell me, does this guarantee odd number of errors? This is x power 0, x power 1, x power 2, x power 3, x power 4. X power 4 plus x power 2 plus x power 1 plus 1, right? 0, 1, 2, 3. Huh. Does this guarantee odd number of errors? 1, 2, 3, 4. These are the 4 terms. Okay, we do have a DBMS class also. No, why you can say that it always guarantees? What if okay, this is, since this is even, right? Since this is even, whatever you multiply with this, can this be odd? Maybe, right? Okay, let's see the answer. So this generator is divisible by 1 1, therefore the quotient will be 1 1 0 1. It can always detect odd number of errors. Okay, it can always detect odd number of errors. So let's do one thing. Since we have the class at 6 p.m., so we will be continuing with few questions tomorrow. Okay, and maybe we can just focus more on the PYQs. So this is one of the PYQ in some exam. This is another PYQ. And then delete, they have asked this. Okay, so we will be just focusing more on the PYQ. Actually, this particular CRC CRC analysis is easy. You just need to check whether this generator is able to divide your error or not. If it is able to divide, it is a bad generator. Otherwise, it is a good generator for those errors. Okay, so we will be continuing tomorrow. Okay. So thank you, everyone. Let's just continue this analysis tomorrow. So tomorrow I will just select some few questions which are relevant, because this is the mathematics, and generally they do not focus on too much of the mathematics. So I will just select the relevant questions to us. Okay. So thank you, everyone. Take care. Bye bye.